Welcome to another great cow basic tutorial for the LGT8XM. Today I'm going to be covering inputs and using the ADC for the LGT8F328P. These boards, this is a series of tutorials that I'm going to cover soup to nuts, and today I'm doing sessions 4 and 5 in one video, inputs and the LDCs. What do they look like? They come on PCBs just like this. I'm going to be using the top green one. That's what we've been using throughout these tutorials. They're a very low cost board with USB connectivity. What does it look like in terms of the circuit? The circuit's relatively simple, but what we're doing is essentially adding components onto the board. In the previous, we've added LEDs and resistors, and then today we're going to be adding in the switch here, and then finally an ADC. How do we go about doing that? Is we have the board, the little nano board, pushed into a breadboard, and previously we've connected up the LEDs, and today, as I said, we're going to add in the switch here and a potentiometer. I'm going to show you that actually on the real board here beside me. So this is the actual nano board. I've got my switch in the same position. It's red on the PowerPoint now, and I've got my potentiometer here, not at the bottom, okay, just don't have the space for it on here, okay. So we're going to be using this in a moment to do exactly what I'm doing here. I'm going to change the pulse rate of the LEDs, but we're going to start with a switch, so I'm just going to disconnect that potentiometer and put that over there. The difference here today is I've actually hidden the small connections to the LEDs under the PCB of the Nano just to get them out of the way to make it clear for us. It's a very simple circuit and very easily set up as you can see. So today we're going to use the switch as an input to set the state of the LEDs, and it says an example as an input. Why do you need to do this is because you need a very small circuit to support this, and that circuit is relatively simple. You need a pull-up resistor. I used 10K. You need the button, which you can see on the PCB, and you need to attach that into the input pin, which, as I said before, is A7 on that nano, which equates to port E3 on the board, it's on the chip itself. So let's have a look at some code to see how this all works. Well, previously to this, we've seen how we define the chip by saying hash chip and then the physical chip name, and option explicit means that we have to declare our variables. Previously, we've learned how to set up a set of constants called LED1 to LED4 to refer to the ports to which the LEDs are attached. So today, I'm adding in new pieces of code. And I'll just push those down so we can see. I've defined a switch, a constant for the switch. The switch is on port E3. I've defined a switch constant called switch. I've defined a small LED delay of 10, and that's another constant. And as before, we've set the LEDs to the out, and that is about it in terms of the LED control for setting them as outputs. I'm going to set my switch as an input because that's what I'm doing. I have the LED going out, 4 of them, and 1 LED coming in. And all I'm saying is here is set the switch, set LED1 to not the switch, so set it to the opposite of the switch. When I push the switch down, it will go to a 1 and vice versa. And then all I'm doing is doing exactly the same for the other LEDs. I'm saying set LED2 to the state of LED1, LED3 to the state of LED2. So essentially, whatever I set LED1 to, it will cascade through to 3, 2, 3, and 4 LED. So in recap, I'm going to push the switch. LED1 is going to be set to either on or off, and then the other LEDs will be the same state. Let's program them up and see what happens on the board. It's as simple as that. It's already programmed it. Here's my finger. If I push the button, 4 LEDs come on. If I let it go, 4 LEDs come off. Now, this looks relatively simple. It is. You set the input of the switch to an in, and then set the value of this port to the first LED, and then they replicate through. It's extremely simple to use inputs with Great Cow Basic. So you can refer it to it as a constant or the port direct. In some of the code that you'll be seeing, that is set up automatically. But I want to make sure that you understand that a switch needs to be an input, and to make it an input, you simply say in. To make it an output, you use the word out. And this will set up the direction of the port for you. Let's just rock back to PowerPoint for a moment to see what we're going to cover next. Well, we're now going to connect up a potentiometer to set the timing of how long it takes us to rotate the LEDs. Yesterday we saw how to rotate the LEDs through the bits of the LED. So there was LED 1, 2, 3 and 4 sequentially were on or off. So I'm going to hook up a potentiometer, and that potentiometer is hooked up to LED the port A6, or it's called A6, or it could be E1, but we have to refer to it as ADC6, and I'll show you why in a moment. And how have I got it connected? I've got it connected up to I've got it connected up here to the chip. I have it connected with 3 connectors, one to 5 volts, one to ground, and then the middle pin goes out into the ADC. And we can see that on the board here. On the board, you can see there's a red wire. Look on the bottom left of the PCB. There's a black wire, and there's a white wire that I removed. I'm just going to reconnect that now and push it back into here. As it stands at the moment, it's got the old program in there. So let's have a look of why that's ADC6, shall we? We should do that. Well, here's the PCB layout we saw before. Let's zoom in on that for a moment. And if I need to zoom a bit more, I think, so we can all see it. Well, we can see there's a whole series of ADCs on here, and they're all in green. So ADCs, there's a whole series of them in here. Let's zoom in a bit further. There we go. Look. Here is the port that we've got it connected to. We've got it connected to A6. Therefore, we have to refer to it as ADC6. So when we talk to it in our program, we're going to talk to it as ADC6. So that's our connection. Let's have a look at the code to make this work. It's relatively simple. We're going to have the same LED setup and the chip setup at the beginning. That's exactly as it was before. I've got a variable, and this variable is quite important because I'm going to be using this byte variable called read ADC value to store the ADC. And the ADC in this particular case is going to be 0 to 255, and I can get that within the constraints of a byte variable. I'm going to be using larger ADC reads tomorrow. I then have a simple do loop, and that do loop will make it go forever. And I'm going to read the ADC6 using the read AD command, and I'm going to place it inside of my variable that I have defined. So the ADC will go up and down, and I'm going to put the content of that inside of read ADC value. I'm going to miss this line here called scale. I'll come back to that in a moment, because the meat of this is wait read ADC so many milliseconds. And that's all it's going to do. It's going to take the value of the byte variable and just make it wait. So if I just program that, and I'll show you that extra command in a moment, we can look what it does out on the board. The LEDs are flashing. If I rotate the potentiometer, they get faster until they look like they're constantly on, or they're at their slowest value. And their slowest value is wait 255 milliseconds, 255 milliseconds, and the minimum is 1 millisecond. And how do I do that? I do that by using the scale command. and I can scale the value that I'm getting in from my ADC to any value that I wish, by saying if it's the value of 0 to 255, convert it into a value of 1 to 255, because a weight of 0 won't work, as you'll figure out later on as you use this language. So it's not a quirk of this language. A weight of 0 is a weight of 0, and it looks a bit stupid in a demonstration. So all this code does is read the ADC, put it in my variable, and then I use that in the wait command to make the LEDs flash. Let me rotate the pot once more, and as you can see, it's rotating. This is fantastic. Let's go back to the third part of the tutorial, which is something to do with the switch. Well, it's about switch debouncing. We saw this type of circuit before, where I've got a pull-up variable connected to my input port, connected to my switch. In reality, when I was showing that demonstration earlier on, in this session, I push the switch doesn't literally go on or off, it bounces. And this is a typical signal. I've actually got the oscilloscope hooked up here as well. I can see that I have a very similar signal to, let me try and redraw it. I can see on my oscilloscope here a line that goes like this. That's a fair representation. And what's happening is the signal is bouncing, and we need to prevent that, especially on this chip. Why? Because this chip is very fast, and as these signals come in and change state, you need to ensure that inside of the switch there are moving parts, that you measure it effectively. So you need to be cognizant of this, make some delays, make some analysis, and I'm going to show you a little program to stop switch debouncing. So the third part of what I want to show you is this switch debounce. Well, out on the PCB, I've actually got I've got my switch attached here, and I'm just going to run a little program. I'm going to put it in. I'm just going to program it up, and it won't look a lot different, but then I'm going to talk through it. So I'm going to program it. Now, when I push the LED, just so you know what happens, you can see the LEDs are coming on and off, but it's actually very different from the simple one that we looked at initially. Yep, it has the same setup in terms of the chip, the ports, and all the inputs, but after that, it's slightly different. Why? Because I have a function. I've defined a function, and I've said to it, go and run a function, and a function is a method of calling another part of the program to give you a result back, and from that result you can do a test. So I'm going to call my special function, and I've called it key pressed, and if it is true, then turn the LEDs on, all of them, or turn them off else. So if it's true, turn them on, else, which means it's false, turn them all off. So I've consolidated lines here, but I've introduced a few concepts. The if then statement, if then else, that means if something is true, do something, else do something else. But plus I've introduced the concept of this function, and a function, as I said, returns a value. This one is true or false. So how does that work? It essentially is going to detect that the button is pushed down. When the button is pushed down initially, it's going to count for 25 milliseconds to ensure that the switch is still down, and after those 25 milliseconds, if it's still down, it will release from itself from the function and return the value true. Otherwise, it will be false. So if we look at the code, I've defined a variable called byte counter, a couple of constants, one called button count max, and the state of the switch when it's down, which is 0. You might want to change that yourself later on. So a function needs to return a value. So the first thing it's going to do is return a false value. So I've set the function return to be false. Later on, I'm going to set it to true if it's true. Well, as I said, I can do some tests in here now. So I do a test, an if-then test. If the switch is down, then do something. If switch equals down, then do something. I set a button counter to 0, and while the switch is down, whilst it's held down, and if it bounces up and down during one of these tests, it's not down. The function will release and return as false. It will wait for 5 milliseconds, increment the button counter, and once the button counter reaches 5, which is the variable we set up here in terms of the constant, it will then set it to true, and then it will exit our function. So it says the button is down, it counts 5 times for 5 seconds, so the button has to be pushed for 25 milliseconds. Then it will exit out with a true statement, else it's false. So if we now look at that again, I can see that there's a small, there is a, it operates as expected. But what we can do is let's do something silly here. We're going to make the wait 50 milliseconds, and I'm going to push the button down and pull it up before 250 milliseconds has gone, and you will see that it looks like the button isn't, that was faster than 250 milliseconds clearly. I'm pushing the button and I'm getting no response. The first time I got one is because I held it down for more than 250 milliseconds. Later on, we'll show you how to write an interrupt routine to do the same. Put that back into something meaningful. So what have we looked at today? We've covered using an input in terms of, we've covered using a switch as an input, we covered an ADC, and we've covered debouncing a circuit. This chip is extremely powerful. Some of these techniques are quite useful because you're using less memory than conventional languages, but you need to look at using the ADC. That's a quite useful function, plus debouncing this circuit is crucial because of the speed of these microcontrollers. So that's the end of this tutorial. I hope you enjoy it. Thank you.